When working with built-in widgets, you simply call their constructors and pass the parameters you are interested in. These widgets can also be combined or nested to build more complex interfaces. Now, let's look at how to define a custom stateless widget. We will create a class named element that extends stateless widget. Because it inherits from stateless widget, we must override the build method, which determines what gets displayed on the screen. Like any Dart class, we can define a constructor and include attributes to represent the widget's internal data. In our example, we use a compact constructor with named parameters enclosed in curly braces. This makes the parameters optional, allowing users to specify only the ones they need. Each parameter also has a default value, reinforcing their optional nature. Since Flutter widgets are immutable, the constructor returns a const object when applicable. Also included is the key parameter, inherited from the superclass, which Flutter uses to keep track of widgets in the tree and maintain their identity. By default, our widget displays an orange rectangle measuring 80 by 60 pixels. These values are assigned via 3 final fields that match the constructor parameters, ensuring immutability. The build method always follows the same pattern. It receives a build context and returns a widget. The context holds details about the widget's position in the tree. In this case, the build method returns a container, and its width, height, and color are set using the constructor parameters. Note that, unlike width and height, the color needs to be wrapped in a box decoration, which lets us define visual styles like background and borders. Here, the border defaults to black on all sides. To get this widget working and replicate the result shown in the iPhone simulator, we need a complete Flutter application. As we have already seen, every Flutter app starts by importing the required packages, at a minimum the material design package. After that, we define the main function, which serves as the program's entry point, and launches the app. To build the app structure, we define a new stateless widget called myApp. Since it extends stateless widget, we override the build method, which returns a widget, in this case, a fully set up material app. The layout follows a familiar pattern. The material app contains a scaffold, which includes an app bar and a body. The widget displayed in the center of the screen is now our custom element widget. Instead of relying on single elements, we can build rich and complex UIs by combining multiple predefined or custom widgets. These can be either stateless or stateful, and their composition only needs to respect a few functional principles. Layout widgets like row and column allow us to position elements horizontally or vertically. Since these are widgets themselves, they can be freely nested and combined to form more elaborate designs. The example presented, taken from the official Flutter documentation, shows a layout structure around a column containing 4 main components. The first is a simple image, while the fourth is a multi-line text. Between them are 2 row widgets. The first row includes a column with 2 text lines, followed by an icon, and the third text widget. The second row holds 3 individual column widgets, each with an icon and the text label stacked vertically. When the row and column aren't sufficient, we can use a stack to layer widgets on top of each other, enabling more complex visual arrangements. Still, it's important to be cautious. Overly deep nesting or unnecessary complex layouts can impact performance, so careful design remains essential. Looking specifically at the second row, we see that each column is made up of an icon and the text label. While this setup is relatively simple, achieving a more refined layout requires accounting for the varying dimensions of these elements. Text labels, for instance, don't all occupy the same space. In fact, labels with 5 characters will typically be wider than those with 4, depending on the font and characters used. These differences can cause misalignment and reduce the visual balance of the interface. To gain better control over sizing and alignment, we can introduce container widgets. Unlike text widgets, which adapt to their content, containers allow you to explicitly set dimensions. That's why in the layout diagram, the pink nodes represent containers used to manage size and spacing, while the light blue nodes show the actual content. By wrapping each column in its own container, we ensure consistent width across all 3 regardless of the text length. A similar container is also placed at the top level of the widget tree to maintain uniformity throughout the overall layout. Now we need to analyze the composition problem in detail.